Welcome to the second lesson of the 7th module, which is on deflection of beams part 2. In the last lesson, we have introduced the concept of deflection of beams, and also it has been introduced that how deflection of beams plays an important role in the engineering structures. We have derived the equation, the differential equation for the elastic curve, and subsequently we have derived the equation for the elastic curve, and we have seen that how to compute the deflection of beam at any point for a particular kind of loading. Now, in this particular lesson we will be discussing some more aspects of the deflection of beams for different types of beams and subjected to different kinds of loads. It is expected that once this particular lesson is completed, one should be able to understand the concept of deflection of beams under different loading conditions for different types of beams. In fact, last time we had looked into simply supported beams subjected to loads. Here we will be looking into some more types of beams with different kinds of loading systems. One should be in a position to understand the concept of superposition method. We will discuss this particular method, the superposition, how to evaluate the deflection if you have more number of loads which are acting simultaneously in a beam, and also one should be in a position to evaluate deflections in different types of beams for different loadings. Hence, the scope of this particular lesson includes recapitulation of previous lesson, which we generally do through the question answer session. We will be looking into the answers of the questions which I have posed last time, and in the process we will be able to recollect whatever we have discussed in the last lesson. We will look into the concept of deflection of beams for different loading, concept of superposition method, and also it includes examples for evaluation of deflection in different types of beams for different loadings. Well, the questions which were posed last time, there the first question is that what is the differential equation of elastic curve in a beam. Now, if you remember last time we had derived that if a beam is subjected to transverse loading, then it undergoes bending, and therefore, the axis of the beam, if we look into it, deforms, and we have seen that in terms of curvature of this particular beam, 1 by rho is called as curvature, which we can write as d2y dx2, where y is the deflection of the beam with respect to its original position. Now, and subsequently, as we had seen, the curvature was related to the bending moment at any cross section m, which is a function of x. Hence, the curvature can be related to the bending moment through this expression, which is E I d2y dx2 equals to m, and this particular equation, differential equation, is called as the differential equation of elastic curve. So, when we mean that the differential equation of the beam bending, then this is the expression which we use, E I d2y dx2 equals to m, and from this particular basic equation we go for the other derived units, like as we know that V, the shear force, is equals to minus dm dx. Hence, if we take the derivative of this particular expression, we have E I d3y dx3, this is equals to minus V, and as we know that q is equals to dV dx, where q is the loading on the beam, the uniformly distributed load q. So, we can, if we take the derivative of this, we get E I d4y dx4 is equals to minus q, and this we have seen last time while deriving the these governing equations, wherein E I is a parameter which we call as flexural rigidity. Now, the second question posed was what is the equation of elastic curve. Now, the first question is the what is the differential equation of elastic curve, and second question is what is the equation of elastic curve of beams. Now, subsequently once we get the differential equation for the beam, which is E I d2y dx2 is equals to moment. Now, if we integrate it once, then we get that E I dy dx, y dash is dy dx, is equals to integral m dx plus a constant C 1, and further integration of this gives us E I y is equals to double integral m dx plus C 1 x plus C 2, where C 1 and C 2 are the unknown constants which are to be evaluated from the boundary conditions. Now, from these we can write that y is equals to 1 by E I integral m dx plus C 1 x plus C 2. Now, this particular expression is termed as the elastic equation of the elastic curve, that y we are representing, since moment m is a function of x, y will get as a function of x. So, that we can compute the value of y at any point along the length of the beam, because if we consider the origin of the coordinate axis at the left hand support, then along the length of the beam as we go at any x we can compute the value of y, and from this particular equation which we call as equation of elastic curve. Now, the third question or the last question posed was, what is the value of maximum deflection in a simply supported beam subjected to uniformly distributed load of intensity W. Now, last time we had evaluated the expression for the elastic curve and subsequently the deflection at different point. Now, for a simply supported beam, when the load is W per unit length along the entire span or the entire length of the beam, the expression for the elastic curve, as we have done from the expression of E I equals E I d 2 y dx 2 equals to the moment. If we do that, we can get the value of y as a function of x, and then if we evaluate the value of y at x equals to L by 2, y at x equals to L by 2, we get the expression as y equals to 5 W L 4 by 384 E I. Now, this particular beam is symmetrically loaded, and hence and as we do not have any horizontal reactive force over here, the vertical reactive force R A and R B we have, R A here and R B over here. Now, for the symmetrically loaded beam, the maximum deflection occurs at the center. In fact, for the elastic curve, if we draw a tangent to the elastic curve at this particular point, this becomes horizontal. So, the point where the tangent to the elastic curve is a horizontal one, that point the deflection we get as maximum. So, the maximum deflection in this particular case is at x equals to L by 2, which is equals to 5 W L 4 by 384 E I. So, this is the maximum value of the deflection for a simply supported beam subjected to uniformly distributed load. So, for a simply supported beam subjected to uniformly distributed load, the maximum deflection occurs at the center of the beam, and the magnitude of that is equals to 5 times W L to the power 4 by 384 E I, where E I is constant throughout the beam, which we have termed as the flexural rigidity. Well, after looking into these questions, let us look into another aspect of this evaluation of deflection. Now, this particular method we call as a superposition method, wherein if you have a number of loadings on a beam. Now, so far what we have seen is that a beam is subjected to uniformly distributed load, or you have a concentrated load at any point in the beam, then we can compute the expression for the elastic curve. Now, supposing if we have a beam wherein there are several loads acting on a beam, there could be uniformly distributed load and several concentrated loads acting, then if we like to compute the deflection of the beam at any point, then of course, we can use the methodology as we have discussed so far. That means, at any section we can compute the bending moment, and as usual we define the different segments over which that moment expression is valid, and then we employ the differential equation of the elastic curve, which is E I d 2 y dx 2 equals to moment, and the validity of that moment expression segment wise, and we can compute the value of deflection with the appropriate boundary conditions. So, this particular technique we can employ and we can evaluate the deflection at any point in the beam. Now, since we are dealing with the beams which are in the elastic stage, it is a linear elastic condition of the beam. Also, if you look into the differential equations, they are in a linear function of the loading. Hence, we can compute the deflection at a particular point for individual such loadings, and we can combine them together to obtain the deflection at a particular point, or we can superpose the effect of different loads at a particular point. In fact, that is what we call as the superposition technique or superposition method. Now, so superposition method is the deflection of a beam produced by several different loads acting simultaneously can be obtained by superposing the deflections produced by the same loads acting separately. Now, as an example, if you look into, this is a simply supported beam hinged at this end and this is on the roller on the other end, and it is subjected to uniformly distributed load Q per unit length, and also it has two concentrated loads P 1 and P 2, which are acting at a distance of A from left support, and P 2 is acting at a distance of B from the right support. Now, when we have these loadings, supposing if we are interested to evaluate the deflection of this beam at this particular point, let us call this point as C. Now, if we like to find out the deflection delta at C, now as I said that we can employ the governing differential equation, which is E I d 2 y dx 2 is equals to moment, and based on this loading over here we can divide the whole beam in 3 segments. The segment 1 is from here to here, just on the left hand side of this concentrated load. Segment 2 is from here to, or from this point to this point, which is from A to L minus B, and the third segment is after this loading to the end of this, and at these 3 places we can take the free body diagram and compute the moment at these 3 places, and consequently if we substitute in this particular expression for the differential equation, we can obtain the value of y with appropriate boundary conditions for the different segments. Also, we can compute the value, and accordingly at y we can compute from this expression for y, which we will get as a function of x. So, at a distance from here, if we know this value of x, we can compute the value of y. Now, also what we can do is we can compute the value of delta c by taking these loads acting individually. Now, instead of these two concentrated load and the uniformly distributed load acting simultaneously, if we assume, let us say that instead of the concentrated loads, now only the uniformly distributed load is acting. Now, if the uniformly distributed load is acting, we have seen how to compute the expression for the elastic curve. Now, in that expression if we substitute the value of x, we can get the value of deflection at point C, which is delta c for uniformly distributed load. Let us call that as delta c 1. So, that is for the uniformly distributed load. Now, next let us consider that it is acted on by the concentrated load P 1 and no other loads are acting. So, now first we are considering that it is subjected to uniformly distributed load. Second, we are considering that there is neither uniformly distributed load nor the other concentrated load P 2, but it is subjected to only concentrated load P 1. Now, for this particular condition again we can solve the differential equation, we can get the expression for y in the beam, and accordingly we can compute the deflection at point C for this load alone, and let us call that as delta c 2. The deflection at C for the concentrated load P 1 is delta c 2. Now, thirdly we assume that this particular beam is subjected to a concentrated load P 2 and no other loads are there, like neither the uniformly distributed load nor the concentrated load P 1. So, if the beam is subjected to only concentrated load P 2, again we can solve the differential equation and compute or arrive at the expression for y as a function of x, and then we can compute the value of deflection at C from this differential for the equation of elastic curve, that what will be the deflection at point C, and let us call that deflection as delta c 3. So, if we add these 3 deflections together, delta c 1 plus delta c 2 plus delta c 3, we will get the total value of the deflection delta c, which otherwise we have obtained from the expression of the elastic curve, had we had taken the loading, all the loading simultaneously. So, this is what we call as the method of superposition, where we can compute the deflection at any point in the beam when we take the simultaneous or the many loads which are acting on a beam. Individually we take the loads and their effects on a particular point we consider, and if we sum them up we can get the deflection of that particular point for all the loads when they are acting simultaneously on the beam, and this is what we call as the superposition method. Well, now let us look into the examples for evaluating the deflection at different points. Now, the last lesson we started with this particular problem, wherein we had a simply supported beam which was subjected to a concentrated load P at a distance of A from the left support or B from the right support. Now, what we need to do is that we will have to find out the expression of the elastic curve for this particular loading on this beam, and also we will have to compute the value of the maximum deflection and rotation at the support. Now, the last time we started with evaluating the moment at different points. Now, as I said that the beam we can divide into two segments, segment 1 and segment 2. Now, from 0 to A, this will be guided by one expression of the bending moment, from A to L it will be guided by another expression of the bending moment. But before that what we need to do is that we need to evaluate the reactive forces, and they are say R A and R B, and since there are no horizontal forces in the beam. So, the value of the horizontal force is equals to 0, and we can compute the value of R A and R B. If we take moment about B, we get the value of R A, and from R A plus R B equals to P, we can compute the value of R B. Now, if you compute the value of R A and R B, they come like this, that R A is equals to P B by L and R B equals to P A by L. This in fact, we had seen last time. Also, for these two segments, segment 1 and segment 2, we can compute the value of the bending moment. Now, for the segment 1 from 0 to A, if we take a free body over here, if we take a cut and draw the free body of the left support, the free body will be that we have the reactive force over here, and on this cut you have the balancing shear force and the bending moment M and V, and this is R A. So, if we take the moment of all the forces with respect to this particular point, which is at a distance of x from left support. So, M is equals to R A times x, and this is what is written over here, and R A being P B by L. So, M is equals to P B x by L, and this is valid between 0 to A. This expression for the bending moment is valid between 0 to A, but as soon as we go beyond this loading, now this expression of bending moment is no longer valid, because the contribution of this load will come into picture. Now, if we take the segment 2 and if we take a cut over here and draw the free body diagram, then the free body of this is going to be like that. We have the reactive force R A over here, we have the concentrated load P over here, and then on this cut you have the shear force and the bending moment, and this is the distance x from here now, and this being A. So, this particular distance is x minus A. Now, if we take the moment of all the forces with respect to this particular point, the point B or the point C, let us call this cut point as C. Now, moment at C will be equals to R A times x. Now, R A being P B by L. So, P B by L times x minus P times x minus A. So, P times x minus A. So, this is what is the expression for the bending moment, and this expression of the bending moment is valid between this point to the end of this. So, from A to L is the range of x, wherein this particular expression will be used. So, you see that over these two segments we have two expressions for the bending moment. Now, our next step is we substitute these values of the bending moment in our differential equation, which is E I d2y dx2 is equals to moment, and moment is equals to P B x by L. So, this is the range of the validity of this particular expression, and subsequently the other bending moment equation which we have obtained for the other segment, we substitute over here again in this differential equation, which is E I d 2 I dx 2 equals to moment, and the range of validity is between A and L. Now, once we integrate these expressions, we come up with this, that E I dy dx is equals to P b by L. Now, x will give us x square by 2 with a constant of integration C 1, and again the validity is between 0 to A. And for this particular expression, if we integrate, we have E I dy dx is equals to P b by L x square by 2 minus p times x minus a square by 2 plus another integration constant which is C 2, and the validity of this particular expression is between A and L. So, these are the expression for dy dx. Now, if we integrate these expressions further, then we will get the values of y, or the expression for y. Now, if you look into that, the on integration of the first equation, we get E I y is equals to p b by twice L x cube by 3 plus C 1 x plus another constant which we have called as C 3, and the validity range is of x is between 0 and A. Subsequently, the second expression yields E I y is equals to P b by twice L x cube by 3 minus p by 2 x minus a cube by 3 plus C 2 x plus C 4. So, we have another two constants C 3 and C 4 have come in after integrations, and the validity of this particular expression, the value of x ranges between A and L. Now, there are 4 constants C 1, C 3, C 2, C 4, and these 4 constants are to be evaluated from the given boundary conditions, or we know the support conditions of the beam, the loading condition of the beam. Now, we will have to substitute the appropriate boundary conditions, so that we can evaluate the values of C 1, C 2, C 3, C 4. And as we have discussed in the previous lesson, you must be remembering that we can have the boundary conditions, either the static boundary conditions or the kinematic boundary conditions, and that if we impose, we can evaluate the unknown constants. Now, let us look into the what are the boundary conditions that we can impose for evaluating these unknown constants. Now, here if you look into the deflection curve, now this is the axis of the beam and this is the expected deflected profile of the beam. Now, at this point, at the load point, now on the left hand side of the load, as we have seen that one expression is given for the deflection, on the right hand side of the load there is another expression for evaluating the deflection. Now, at this particular point of the load, where this is the limiting or the boundary for the two expressions to be employed. Now, at this particular point, now from the left hand side and from the right hand side, the values should be equal, or what I mean is the deflection of this beam at this particular point, or the slope of the deflection curve at this particular point, from whichever side we compute, either from this side or from this side, they should be the same, because the elastic curve has to be continuous. It is not a discontinuous at the, though we are using two different functions for evaluating moment and correspondingly the deflection curve, but physically the beam segment is not a discontinuous one. So, when it deflects, the deflection curve has a continuity at that particular point, or the boundary point between the two expressions which we are using. So, at that particular point, if we compute the deflection or the slope, whichever expression we use from either side, they should give us the same value. So, we can use this particular condition that at x equals to a, slope on either side or at that particular point is equal, whichever expression you use. At x equals to a, the deflection at that point should be equal, whichever expression you use, and of course, we have these two kinematic conditions, that at x equal to 0, y equals to 0, and at x equal to L, y is equals to 0. Now, if we substitute that at x equals to a, slope is equal, then from the expression of dy dx, in fact, if you look into the expression of dy dx as we have obtained as P b by L x square by 2. So, x is equals to a. So, P b by twice L a square, and this particular expression, since x is equals to a, so this goes up. So, there also we have P b by twice L a square. So, if you substitute that, then we get that P b x square by twice L at C 1. Of course, this is a, because we are substituting x equals to a, and so as this x equals to a, this is a square. So, this gives us the value of constants, that means a relationship between C 1 and C 2, we get C 1 is equals to C 2. Now, if we consider the second of the boundary condition, that at x equals to a deflection is equal, that means, if we employ these two equations now, whichever equation we use at this particular point, deflection should be same from either side. So, if we substitute x equals to a over here. So, this is P b a cube by 6 L plus C 1 times a plus C 3 is equals to P b a cube by 6 L plus C 2 a plus C 4. Now, these two terms being same identical. So, that gets cancelled. Now, C 3 is equals to C 4 and C 1 equals to C 2 we have already seen earlier. So, the C 1 a and C 2 a also gets cancelled. So, this gives us C 3 is equals to C 4. Now, if we substitute this particular boundary conditions, that at x equals to 0, y equals to 0, at x equals to 0, y equals to 0 means we will have to use the first of the expression, since it is valid between 0 to a, and that gives us that C 3 equals to 0. Now, since C 3 is equals to C 4, so C 3 and C 4 both are equals to 0. From this expression we get C 3 equals to 0, and since C 3 is equals to C 4. So, C 3 equals to C 4 equals to 0. Now, if we employ the last boundary condition, which is at x equals to L, y is equals to 0. Now, again the validity of this particular boundary condition will be with respect to this particular expression, because this expression of y is valid between a to L. So, if we substitute the value of x as L in the second of expression, and since we have already seen that C 3 and C 4 equals to 0. So, we are left with C 2 only, and if we substitute the value of x as L, we get the value of C 2 as equals to minus P b by 6 L times L square minus b square. So, this is the expression which we get once we substitute the value of x as L. Now, so all the unknown constants now are evaluated except C 2 and C 1, since C 1 is equals to C 2. So, C 1 and C 2 will be existing, and C 3, C 4 are 0. Now, once you substitute this value of C 2, then the expression for the deflection curve comes like this, that E I y is equals to P b x cube by 6 L minus P by 6 x minus a cube minus P b by 6 L L square minus b square x. This is the value of C 2, this is for the second part, and for the other part we substitute the value of C 1 and we get the expression for E I y. So, we can now get the expression for the deflection curve. So, y as a function of x, and at any point now from these two sets of the deflection curve which we have, or the equation of the deflection curve as we have from 0 to a and a to L, we make use of these two expressions and we compute the value of y at any point in the beam. Now, if we like to find out the slopes at the two ends at n a and n b, now theta a from the first of expression we can compute, and we get the values of dy dx as P b by 6 E I L L square minus b square, noting that L minus a as equals to b, and if we substitute we can get the value of theta a, and theta b accordingly if we substitute or in the expression of dy dx as we have obtained earlier, if we substitute for x equals to L, we get the value of theta at b, and we get P a b by 6 E I L L plus a. Now, here if you look into the sign of this theta b is positive, whereas theta a is negative, and as you have seen that we have earlier noticed it, that if you have the deflection curve and if we take the tangent at this particular point, this is moving in a clockwise fashion with respect to the original axis of the beam, and because it is clockwise according to our sign convention, this is minus theta a, and if we take a tangent over here, this moves in an anticlockwise direction, and according to our sign convention, this is plus theta at b, and the values of these are given by this particular expression. And as we have seen that the loading is placed at a distance of a from the left support or b from the right support. So, it is not symmetrically loaded. Now, as in the previous case or the first case where we have taken that a beam is loaded over the entire length of the beam with uniformly distributed load, where we said that the beam is symmetrically loaded, and hence we had obtained the maximum value of the deflection at the center, where the tangent to the deflection curve is horizontal. Now, at this particular problem, since the loading is not symmetrical, hence we need to find out the position of the maximum bending moment. Now, for evaluating to find out the position for maximum deflection in the beam. Now, for finding out the position for the maximum deflection, we need the criteria which we adopt is that the tangent which we draw to the elastic curve must be horizontal, or in other words the value of dy dx at that particular point should be equals to 0. So, if we adopt the value of dy dx equals to 0, you can compute the value of the value of x where the tangent is horizontal, and once you substitute the value of x in the expression for y, you can get the value of deflection curve which is y, or deflection at that particular point. Now, let us look into this particular aspect of this beam, as we have evaluated that the deflection for the segment 1 is E I y is equals to P b x cube by 6 L minus P b by 6 L into L square minus b square into x, and for the segment 2 we have E I y is equals to P b x cube by 6 L minus P by 6 into x minus a cube minus P b by 6 L into L square minus b square into x, and consequently the values of the rotations at end A is theta a and at end B is theta b, and as we have seen that at theta a is negative and theta b is positive, as I have explained already to you. Now, let us look into the case of a particular situation when this particular load, which is located now at a distance of a, if we try to place this at the central position, means that the values of a and b, if they are equal and is equals to L by 2. So, if we substitute the value of a and b as L by 2, we get the situation where the beam is subjected to a load, a concentrated load which is acting at the center of the beam, and thereby the distances from the two ends is equals to L by 2. Hence, that gives us a particular situation of this generalized loading situation. Now, if we substitute the values of b and a as L by 2, then we get the expressions like this, that when the load P is acting at the center of the beam, thereby A is equals to L by 2 and B is equals to L by 2. Hence, the value of E I y, which was general so long with the values of A and B, now becomes a function of L alone, and of course, with the value of x along the length of the beam, and value of E I y is equals to P x cube by 12 minus P L square x by 16, and which if we take P x by 48 out, it becomes 4 x square minus 3 L square. Now, as you can see here that this particular expression is little different than what we have evaluated in case of the general expression, where P was located at a distance of A from the left support. Now, this particular expression is valid between 0 to L by 2. When the value of x lies between 0 to L by 2, this particular expression is used. Now, consequently, if we like to evaluate the deflection at any point between L by 2 to L, then the second of the expression for the general expression will be used, where again for A and B we use value of L by 2, and consequently we see that EIY is equals to Px cube by 12 minus P by 6 into x minus L by 2 cube minus PL square x by 16, and the validity is between L by 2 to L. Now, fortunately the beam is being symmetrical. So, if we compute on one side, we can get the values for the other as well, as we have seen earlier, and for the deflection curve, as it is known that at this point it will be the tangent to the deflection curve will be horizontal, and this will give us the maximum value of the deflection. And consequently, if we substitute the value of x as L by 2, then we get the value of the deflection, maximum deflection of the beam at center, which is equals to PL cube by 48 EI. And if you look into the sign of this, it is negative, that indicates that the beam deflects towards the opposite direction of the positive y, hence the negative sign comes in. So, this is the maximum value of the deflection which is occurring at the center, and consequently, if we substitute the value of x, if we substitute the value of a and b as L by 2 in the expression for theta a and theta b, we will get the values as PL square by 16 EI and minus for theta a and plus for theta b, as we have seen earlier that this is minus theta a and this is plus theta b, and the magnitude of these will be PL square by 16 EI. So, when we talk about the particular case, then delta maximum is PL cube by 48 EI and theta a equals to theta b, magnitude wise it is PL square by 16 EI. Now, let us look into another example wherein we have in fact this particular example we had solved last time, wherein we said that the loading is uniformly distributed over the entire span of the beam. And if you remember that we had started with the differential equation of the elastic curve, which is EI d2y dx2 is equals to the moment, and moment we had computed at any cross section which is at a distance of x from the left support, and consequently we have evaluated the values of the deflection, which is the this is the expression for the differential equation. And then subsequently we came up with that the value of y at x equals to L by 2 is this, and correspondingly the value of theta a n and theta b is this. Now, also you had seen that the derived equation of this governing equation is EI d4y dx4 is equals to minus q, the loading. Now, we can start from this particular point as well, and we can arrive at the value of y and theta a and theta b. Now, let us substitute this or let us start from this particular expression of the differential equation and see what we get. Now, we have EI d4y dx4, this is equals to minus q. Now, if we integrate this, we have EI d3y dx3, this is equals to minus qx plus a constant c1. Now, if we integrate it further, we have EI d2y dx2 is equals to minus q x square by 2 plus c1x plus c2. Now, if we apply the boundary condition here itself, now since we know that c1 and c2 are the two unknown constants, and EI d2y dx2 represents the value of the bending moment. Now, for a simply supported beam, the bending moment at supports for both hinge support and roller support is 0. So, bending moment at x equals to 0, at x equals to 0 d2y dx2 is 0, and also at x equals to L d2y dx2 equals to 0. Now, if we substitute that x equals to 0 d2y dx2 equals to 0, this gives us that C2 is equals to 0. Now, if we substitute this, that at x equals to L d2y dx2 equals to 0, we get C1 into L is equals to q x square by 2, and x is L. So, this is L square by 2. So, L square gets cancelled. So, this gives us that C1 is equals to QL by 2, Hence, the expression here that we get EI d2y dx2, this is equals to QL by 2x minus Q x square by 2. Now, this is the expression of the bending moment which, or the equation which we had started with in the previous case. So, in fact, from this particular point onwards, again if we follow the same steps as we have done earlier for evaluating the deflection curve, equation of the deflection curve, then it will follow the identical situation. So, whether we consider that EI d2y dx2 equals to the bending moment, or we can start from even EI d4y dx4 equals to loading, the finally the solution which will you get, or the expression for the elastic curve which will you get, and consequently the values of the maximum deflections and the rotations at different point as we compute, they will be identical. So, this is the expression which we had in fact used it. If you look into that QL by 2x minus Qx square by 2 for the bending moment, based on which we had obtained the values of deflection and the rotations. So, we can adopt either the EI d2y dx2 equals to moment, or EI d4y dx4 equals to the minus of the loading. Now, let us look into another example where this is a beam. Now, it is a different type of beam. The beam is fixed at end A and is free at the end B, and thereby as we know that this is a cantilever beam, and this beam is subjected to uniformly distributed load of Q per unit length. Now, what you will have to do is that you will have to determine the equation of the deflection curve of this beam, and you will have to find out the deflection and rotation of the free end, the end B. Now, flexural rigidity EI of this particular beam is constant. So, right through the EI value is the same. Now, for evaluating the deflection curve, or arriving at the expression for the deflection curve, what we need to do as a first step, as we have done before, we need to evaluate the reactive forces. Now, at this fixed end you will have the vertical force, let us call this as RA, you will have the horizontal reactive force, let us call this as HA, you will have the bending moment which is equals to M. Now, if we take the vertical, horizontal and vertical and the moment equilibrium, now summation of horizontal forces equals to 0 will give us HA equals to 0, summation of vertical forces equals to 0 will give that RA which is acting vertically upwards minus Q times L, this is equals to 0. So, that gives us RA is equals to QL, and if we take the moment of all the forces with respect to this particular point, we have the moment value M, let us call M dashed, and QL also will have the moment in the same direction. So, plus Q into L by 2. So, QL square by 2, this is equals to 0. So, this gives us M dashed is equals to minus QL square by 2. So, you will have the value of RA as QL and M dashed as equals to QL square by 2. Now, we follow the same steps as we have done earlier. That means, now we have for this particular beam the reactive values known, which is RA is equals to QL, and we have the moment which is equals to that M dashed is equals to minus QL square by 2, and RA is equals to QL. Now, if I take a section here and if we take the free body of that particular part, so here you have the reactive force, you have the moment, and you have the uniformly distributed load, this is at a distance of x, and on this cut section you have the equilibrating forces, the shear force V and the bending moment M. So, if we take the moment of all the forces with respect to this particular point at the cut section, then we have M which is in an anti-clockwise direction, then we have moment at this support m dashed, which is in a clockwise direction. So, m minus m dashed. Then we have moment due to R A, which is again in a clockwise direction. So, minus R A into x, and the loading which is again in the anticlockwise direction. So, minus q into x times x by 2, which is q x square by 2, this is equals to 0. So, this gives us that value of the moment m is equals to m dashed, which is minus q l square by 2 plus R A into x. So, q l into x plus q, or this minus, this should be plus, because q x square by 2 has a moment in the same direction, the clockwise direction. So, this is going to be equals to minus, so minus q x square by 2. So, this is equals to 0. Sorry, this is the moment expression, this is equals to the moment. Now, if I substitute the value of the moment in the differential equation, so we have E I d2y dx2 is equals to moment, which is q l x minus q l square by 2 minus q x square by 2. Now, if I integrate this, we have E I dy dx, this is equals to q l to x square by 2 minus q l square by 2x minus q by 2 to x cube by 3 plus you will have the constant C1. Now, on further integration we will have E I y, this is equals to q l by 2 and x square will give you x cube by 3 minus q l square by 2 to x square by 2 minus q by 6, x cube will give us x 4 by 4 plus C1 x plus C2. Now, the boundary conditions what we have now, C1 and C2 are the two unknown constants which are to be evaluated from the two boundary conditions, and the boundary conditions here are at x equals to 0, y is equals to 0, and also at x equals to 0, dy dx equals to 0. Now, if we substitute this, that at x equals to 0 dy dx equals to 0, that gives us that C1 equals to 0, and at x equals to 0, if we substitute y equals to 0, then we get that C2 also is equals to 0. So, we get that both C1 and C2 are 0, and hence the expression for the deflection curve y is written in this form, that E I y is equals to q l by 6 x cube minus q l square by 4 x square minus q by 24 x to the power 4. Now, what we need to do is that we need to compute the value of the deflection at this free end and also the slope of this elastic curve at this free end. That means, if we take the tangent of the elastic curve at this particular point, then what is the rotation of this particular point of the elastic curve. Now, so if we substitute the value of x as L, then we get the value of y from here. So, this gives us that E I y is equals to q l by 6 into this x is L. So, L cube minus q L square by 4 times L square minus q L 4 by 24. So, if we combine this together, then we have this as equals to q L 4 this we have 24, then 4 minus 6 minus 1. So, 6 minus 1 7. So, 4 minus 7 is minus 3. So, this is equals to minus q L 4 by 8 will give you the value of E I y. Now, let us remove this part. So, we get the value of y as equals to minus q L 4 by 8 E I. Now, again this minus sign indicates that it is in the opposite direction of the positive y. So, it is deflecting downward, and the magnitude of the deflection at the end, if we know the value of intensity q and the span length L, then q L 4 by 8 E I is the value of the deflection at the tip point or at the free end. Now, we can compute the value of dy dx. In fact, we could substitute in the expression for dy dx the value of x as L, or in fact we can take the derivative of this expression y, from which we can compute the value of dy dx or the slope at the free end. So, E I dy dx is nothing but equals to q L by c into 3 x square minus q L square by 4 twice x minus q by 24 4 x cube. Now, in this if we substitute x equals to L, this gives us q L cube by 2 minus q L cube by 2 minus this is q L cube by 6. So, this is what. So, q L cube by 2, q L cube by 2, this gets cancelled. So, you have minus q L cube by 6 is the, and again as you can see that it is minus, it indicates that the rotation is clockwise, and rightly as we have seen, since the deflected shape is in the negative direction. So, at this point if we draw the tangent, so this gives us a clockwise rotation, and which is minus q L cube by 6. So, dy dx at x equals to L is minus q L cube by 6 E I. Dy dx is equals to minus q L cube by 6 E I. So, this is the value of the slope at the free end, and the deflection at the free end is equals to q L 4 by 8 E I. Well, we have another problem wherein the load is acting at the free end, which is a concentrated load instead of a uniformly distributed load, and exactly in the same way we compute again the reactive forces, the value, say if we call this beam as A and B, we have the reactive force R A, we have the horizontal force H A, and we have the moment M A. Now, here again if we take the horizontal equilibrium, we get H A equals to 0. If we take the vertical equilibrium, we get R A is equals to P, and if we take the moment, then we get that M A is equals to minus P into L. So, these are the values of the reactive forces, and if we take the moment at any cross section for evaluating the deflection curve. Now, so we have here R A is equals to P, the moment M is equals to minus P into L, and R A is equals to P. Hence, if we take a cut over here and draw the free body diagram, then we have the reactive force this as R A, the moment here as M A, and here we have the shear force and the moment M. So, if we take the moment of all the forces here, we have M, this is M A is minus R A into x, this is equals to 0, and hence M is equals to R A into x, which is P into x plus M A, which is minus P L. Now, if we substitute this, that means if we have E I d2y dx2, this is equals to P x minus P L, then we get E I dy dx, this is equals to P x square by 2 minus P L x plus C 1, and E I y is equals to P by 2 to x cube by 3 minus P L x square by 2 plus C 1 x plus C 2, and C 1 C 2 can be evaluated from the boundary conditions again. At x equals to 0, dy dx 0, at x equal to 0, y also is 0. So, at x equal to 0, dy dx 0 will give C 1 equals to 0, and at x equals to 0, y 0 gives us C 2 equals to 0. Hence, we have that E I y is equals to we get the values that E I y is equals to P x cube by 6 and minus P L x square by 2, and at x equals to L, if we substitute the value, we will get the value of y. So, E I y is equals to P L cube by 6 minus P L cube by 2. So, this gives us that minus P L cube by 3. So, P L cube by 3 I is the displacement, and we can compute the value of dy dx, substituting the value of L, we get the value of the rotation at the end. So, this is how we compute the value of the deflection and the rotation, and this is an example which is given for you. In fact, as we have discussed today that how to employ the method of superposition, we can employ the method of superposition in this particular case, and you can compute the value of the deflection at any point. We will discuss this problem next time. Now, to summarize then, in this particular lesson we have included the following, that we have recapitulated the previous lesson, we have introduced the concept of deflection of beams for different loadings, and then the concept of superposition method we have discussed, and some examples to evaluate deflection of different types of beams for different loadings. And these are the questions set for you, that what is flexural rigidity of beams, please explain, and what is meant by M by EI diagram, and what is the value of maximum deflection in a simply supported beam subjected to concentrated load P at the center. We will discuss the answers of these in the next lesson. Thank you.